So in this video, we're going to complete section 2.1. This is really some just miscellaneous things that we need to know that will come up through the semester, and it's going to be an introduction to some of the proofs. Linear, in this course, we're going to see a lot of proofs, especially when we get to chapter 4 on vector spaces, because you're going to have to prove whether or not something is a vector space. So we're just going to jump right on in with the last couple of problems in section 2.1 with proofs. So first off, we're going to talk about the trace. So when we talk about the trace of a matrix, it has to be a square matrix. Notice the dimensions here. And the trace is defined to be the sum of everything down the main diagonal. So if we wanted to write that mathematically, we could think about it this way. Remember, every entry in a matrix can be written in terms of IJ notation. But if I want the entries down that main diagonal, then we're talking about the A11 section, the A22 section, the A33 section, and so on. So we could write this as AII, where I is going to go from 1 to N. So the trace is just the sum of all those numbers. So the trace is pretty easy to deal with. If we're looking at 63, the trace is really just going to be the sum of these three numbers. So if I were to take those and I were to add them together, 1 minus 2 plus 3 ends up being 2. So we would say that the trace, I'll write it this way, the trace of A is 2. In 64, this is an identity matrix. It's a square 3 by 3. And notice we have zeros everywhere except that main diagonal. So if we were to find the trace for this guy, all we're going to do is add those elements down that main diagonal, and we're going to get the trace as 3. So that matrix in 64 is called a diagonal matrix. A diagonal matrix is a matrix that has zeros everywhere except maybe entries along that diagonal. And that leads us into the next question or set of questions. So if we want to talk about the product for diagonal matrices, it's really pretty easy to find that product. Because what will happen is that you end up really just multiplying what's going on down that main diagonal, because all those zeros will cancel out a lot of different pieces. Let's look at a few examples. Let's look at 57. So in this case, we want to find A times A, which is really A squared. So check out what's going to happen. So we have negative 1, 0, 0, 0, 2, 0, 0, 0, 3. And we're multiplying it by itself. So we have a 3 by 3 multiplied by a 3 by 3. Since the inside dimensions match, it is defined. And we're going to result in a 3 by 3 matrix. 3 by 3s have non-entries. So to get that first entry, we're going to go first column, first row of the first matrix times first column of the second matrix. So when we multiply, negative 1 times negative 1 is a positive 1. And then we're going to be multiplying by zeros here and then here. And we're going to add all those together. But notice that the answer is really just going to be negative 1 times negative 1 plus 0 plus 0, which is just going to be a positive 1. Now we're going to multiply here and here. So we're going to have 0 plus 0 plus 0. And then we're going to multiply first row by last column. So we're going to have 0, 0, 0. So the only entry in that row is in that first row, first column, that top left-hand corner. Now let's move to the second row. So now we've got second row, first column. So it's going to be 0 plus 0 plus 0. Second row, second column, 0 plus 4 plus 0. And then second row, third column, 0 plus 0 plus 0 is 0. And then to get entries in that last column, we're going to multiply last row. We're going to multiply last row by first column. We're going to get a 0 there, a 0 there, and then we're going to get a none there. So what happened is we ended up with another diagonal matrix with entries just down that main diagonal. So there's some shortcuts that you can start to see happen when we have really specific types of matrices, like diagonal matrices. An easy way to do that is we end up really just multiplying those entries down that main diagonal. Now, that happens because we have a specific type of matrix. And we're going to go through and we're going to prove that in just a second, just for fun. So if that works for 57, what do you think would work for 58 when we have this matrix? Well, if we want to find a times a, which is really just a squared, since this is a diagonal matrix, then all we have to do is just multiply down those main entries, down the main diagonal. So it will be 2 times 2, which will be 4. Negative 3 times negative 3 is a 9. And then 0 times 0 is 0. So we really just end up squaring those entries down that main diagonal. And then we're going to have zeros everywhere else. If we wanted to, we could go through, we could do it the same way we did it up here, and we would get the same answer. So what I want to do now is I want to prove that. So we're going to come up with 2 generic matrices, and I'm going to do 3 by 3s. If we wanted to prove this generically for all matrices, we could do that with n by n matrices. But since we're just starting proving things, I'm going to go with just a 3 by 3. So if we have a diagonal matrix A, we're only going to have entries down that main diagonal. So I'm going to have a matrix A here. So A squared, by definition, would be A times A. And what that would look like here is we're going to have A11, 0, 0, 0, A22, 0, 0, 0, A33 times itself. So there's the setup. Now, if we were to multiply this out, notice the multiplication is defined. We have a 3 by 3 times a 3 by 3. Inside dimensions match, which means we end up with a 3 by 3. And 3 by 3s have non-entries. So if we multiply, we're going to go first row, first column. So that's A11 times A11 plus 0 plus 0, which is just A11 squared. If I go down that second column, I'm going to end up with 0. And if I go down that third column, I'll end up with 0. So we're really just multiplying now. It's just now we're multiplying with very generic matrices. So we're going to do the same thing. We're going to use second row, first column. So we're going to have 0. Second row, second column. We're going to see that A22 squared come out if we use the multiplication algorithm. And then third column gives us a 0. And then using that last row, first column, gives us a 0. Second column gives us a 0. But that third column, we would have 0 plus 0 plus A33 times A33, which is A33 squared. So you can see why this works the way it does. It comes out in the proof. So there's the end. And I like to show the end of a proof by drawing just a little square down here with that's shaded in. It lets me know that's the end. Now, what do you think would happen if we change this to a cube? So if we were to change this to a cube, then what would happen in our algorithm is we would multiply 3 times. So then in our proof, we would end up with a cubed here, here, and here down that main entry. So you can see how we can take something really simple and then we can broaden it out even more. So then what do you think would happen if we took 2 matrices, and I'm just going to do 2 by 2s, and I'm going to let them be diagonal. And I wanted to multiply these matrices together. So let's see what's going to happen. So we have A11, 0, 0, A22 multiplied by B11, 0, 0, B22. So we have a 2 by 2 times a 2 by 2. This is defined and we will get a 2 by 2. Which will have 4 entries. So if we use our multiplication algorithm, we're going this row by this column. So that's going to be A11, B11 plus 0. And then we're going to move to the second column. So we're going to have 0 plus 0. And now we're moving to that bottom row. So bottom row, first column would be 0 plus 0. But second column will be 0 plus A22 times B22. So you can see what's happening. This is kind of an informal proof. But you can see what's happening here. If we were to take 2 matrices that are diagonal matrices and we were to multiply them together, we will get another diagonal matrix. And the entries along that diagonal will consist of those entries multiplied together. Here for that first entry, here for that second entry. So diagonal matrices have some pretty cool properties there. So then let's look at 59. In 59, they're giving us 2 diagonal matrices. And they're asking us to find that product. Well, we kind of proved informally above that that product would really just be those entries multiplied together. So let's use that result. 2 times negative 5 would be a negative 10. Negative 3 times 4 would be a negative 12. So there's our product, AB. Now, if we wanted to find BA, we're multiplying in the opposite order. Generally, multiplication is not commutative. However, because we're dealing with diagonal matrices, we're going to get the same result. Because it doesn't matter whether I multiplied 2 times negative 5 or negative 5 times 2, I'm still going to get a 10. And then we're going to have a negative 12 in that bottom right corner. So you can see how we ended up with the same thing, AB or BA. So, like I said, multiplication is generally not commutative. However, in this case, it will be commutative, only for diagonal matrices. So now we're going to look at a couple of proofs. So in 67, we want to prove that the trace of A plus B is equal to the trace of A plus the trace of B. And they're telling us we're going to use square matrices of order n. What that means is we're going to deal with n by n matrices. And then C is a scalar. We don't have a C value here. We don't have to worry about that. Anytime you do a proof, you have to define what you're working with. So here we need two matrices A and B, and they have to be of the size n by n. So we're going to say we're going to let A look like this. And then we're going to let B be similar. But it's just going to have entries B1, 1, B1, 2, and so on. So we want to prove that the trace of A plus B equals the trace of A plus trace of B. So let's look at what the trace of A plus B would look like. So to do that, I'm going to start with A plus B. What would A plus B look like? Well, they're both n by n matrices. So we would just add those like components together in the respective spaces. So top left-hand corner would be A11 plus B11. Then we would have A12 plus B12, and so on. So there's what our sum would look like. And that's based on the definitions of what we chose A and B to look like. So what would the trace be? Well, the trace is the sum of everything down those main diagonals. So it would be the sum of this term plus this term all the way down to this guy. So it would be A11 plus B11 plus A22 plus B22 plus all the way down to ANN plus BNN. What's important there is that those subscripts are all 1, 1, 2, 2. It would be 3, 3, 4, 4, and so on until we get to NN. Now, what's cool is that we're dealing with row numbers, and we can change that grouping. You guys remember the associative property is all about grouping. Well, we can change the grouping and we can change the order. So if I were to add A11 plus B11 plus A22 plus B22, couldn't I group all the A's together? A11 plus A22 plus A33 all the way up to ANN. And then couldn't I group all the B's together? So this is the commutative property. And we can change that order of addition, which would be fine, which means that we can group those A terms together and those B terms together. So there's your associative property. And by definition, this is the trace of A. And this is the trace of B. So our goal was to prove that the trace of A plus B is equal to the trace of A plus trace of B. And we can do that just by defining two matrices, finding that sum, and then finding the trace of that sum, and then playing with those properties of row numbers to go back to that definition of what the trace of A would be and what the trace of B would be. So we proved it. We're done. That second proof, we want to prove that if A and B are diagonal matrices of the same size, then AB is equal to BA. So we showed this for 2x2s, but now we want to show it for any size matrix. So we're going to have to go a little bit bigger, think a little bit broader here. We still need to define two matrices, and they have to be of the same size and they have to be diagonal. So diagonal matrices always have to be square, and they're going to have zeros everywhere except maybe that main diagonal. You can have zeros down the main diagonal, but you just can't have numbers anywhere other than the main diagonal. So there's matrix A, and B is going to be similar. Always keep in mind the goal. In this case, the goal is to prove that A times B is going to equal B times A. So let's look at A times B. And we're just going to use that multiplication algorithm. So we're still going to end up with an n by n. So first row times first column will be A11, B11, plus 0 times 0, plus 0 times 0. So we're going to have a whole bunch of zeros underneath. So we're going to have A11, B11 here, plus 0, plus 0, plus 0, plus 0, which is just going to be A11, B11. So second entry is going to be first row, second column. So we're going to have A11 times 0, which is 0, plus 0 times 0, plus 0 times, 0 times B22, which is 0, plus 0 times 0, plus 0 times 0. So you can kind of see the pattern that's going to come out there. So we're going to have a 0 there. That next entry is going to use that first row in that third column. So A11 times 0 is 0, plus 0 times 0, plus 0 times 0 is 0, and so on. And then first row, last column, we're going to get 0. So you can see what's coming out just using the definition. I'm going to say by definition of matrix multiplication. We have. So now we're in that second row. So we're going to use that second row and we're going to use that first column. Second row times first column is going to give me zeros when I add and multiply. But the second row, second column, we're going to have 0 plus A22, B22, which is A22, B22, plus a whole bunch of zeros. Third column with the second row, third column is going to be 0. So you see, you're just going to get a whole bunch of zeros here. And then if we move to that next one, you're going to see the same kind of thing come out. So third row, first column would be 0 plus 0 plus 0, and so on. Second column, 0 plus 0 plus 0, and so on. Third column, that's where we're going to have something. 0 plus 0 plus A33, B33. plus 0, plus 0, plus 0, and so on. So you can see that pattern coming out, and that's what we're looking for really when we see things in math, patterns. And then that last one, we're going to have 0, 0, 0, all the way down to that last one, which is going to be ANN, BNN. So there's the product AB. Now, we know multiplication under the row numbers is commutative. So A11 times B11 is the same thing as B11 times A11. B22 A22 is the same thing as A22 B22. So we can change that order. This seems like a menial step, but it's actually really important because there are places in mathematics where commutativity does not happen. So we could change that order because row numbers are commutative. So this is the commutative property of row numbers from multiplication. You should always be able to identify why what you're doing in that step happens. And then that is actually the definition of B times A. So there's the end of that proof. Now, these aren't the only way to prove things. I think this is the easiest way to start seeing some of these proofs is just to define your matrices and then brute force that multiplication so you can see what's happening. And it also reinforces that definition of multiplication, which is going to be super important as we proceed through the course. So we're going to see more proofs as we go through the course.